Hello, everybody. Welcome to SRA 365. I'm, of course, Professor S, and this is this week's lecture. So, just to refresh, when we're thinking about p-values and thinking about statistical significance, you're looking at the p-value and determining if it is lower than 0.05. I talked about this last class, so if you want more information on that, make sure you go to at the end of the video, there's a link to the last week's lecture. And it talks more about that there. Another thing, and I keep saying this each week, make sure you're naming the variables correctly. Like, for instance, if the directions say to call the data frame lab7.data, make sure you're calling it that. Also, another thing, too, don't rename objects. If it's called model 1 or whatever, don't call it model 5 or I don't know what else you want to do. Just try to keep things consistent. We have to grade a bunch of these, and changing the names makes it difficult, and points will be taken off if you change some things. If you need more explanation of any of these things, just send an email and we'd be happy to help, but just please keep it consistent. And then the one other thing is like some people have been having issues with installing packages, and I've said this before, but I will say it again. Make sure, like, when you're installing packages, just install the package in its own line. Don't install and load when you're don't select multiple lines. Just run that one line that says install the packages, wait for it to finish, and then run everything else. Okay? I've had the most success with that. So hopefully that will help you. If you have any other issues, let me know. Okay? All right, so now we've talked about simple regression before, and it like kind of follows this model. But what we're thinking about today is multiple regression, where we're using multiple predictors to predict our response, right? And so before, with the simple regression, it was a equation of a line. But really what we're coming up with now is not a line. It's, we're doing slopes and that sort of thing. But technically, this is a multiple dimensional thing, and it's getting to be more than a line, so it doesn't really fit that. I don't know. Maybe I'll continue calling it a line because it's very linear, but technically it's not. Could be a plane. It could be some sort of hypersolid. The thing is it's we're using this equation above, and the thing is, it's like our predictors are going to be, for this week, numeric, or kind of, sorry, I hit the microphone, but anyways, it's not going to be categorical. That's the important thing. So we're not using categorical variables yet. That'll be next week. But anyways, the idea is, let's just keep the categorical variables out of it, and we're going to try to try to pick variables. Now, the thing is like, when we're making these models, some of these predictors work better than others. And so one of the things that we're going to be thinking about this week is thinking about what variables are important. One of them important? Is all of them important? Is two of them? I don't know. That's what we're going to kind of explore. It varies for different models, and we're going to talk about like how do you pick the best predictors for what we're trying to do. And interestingly enough, there's a little bit of subjectivity to this. So, which is kind of going to be weird for some people when thinking about math, because it's usually like it's this or it's this. There's a definite right answer, and we're getting into some gray areas. Anyways, let's kind of talk about how we create this model. So first of all, the model is created very similar to how we were creating our models before, where we use the LM function. But the difference is like each of the predictors, we have one predictor before, and so it's the same thing as that, but we just keep adding the predictors on. That's how we're doing it, and we're still referring to the data frame. And so like when we do that in the walkthrough, in the code that's given in the text, you get this, right? So we do the x1, x2, x3, x4, and x5, and we get this. And this is like the summary part. Sorry, this is what we get from the summary for most of the part of the summary. I did exclude some of the top part. but this is like the part that we like, right? And so like specifically, this is the slopes of the data. This is the coefficient that is tied to like that variable and the predictor, or the response, excuse me, the y value. This is going to be the p-values that are tied to each one of those. And so the idea is like what R does is it tests each one of those slopes, if you will, and it says, all right, how does this compare to this slope not being here, right? Or it being 0. How much does that affect the data? The more that it affects the data, the lower the p-value, right? And so notice that some of these p-values are significantly lower than others, right? And that's like how much it's affected by it being there or not being there, okay? So the more that it's affected, that the lower the p-value, okay? Before we had talked about the multiple r squared is like what we did for when we did one value. For this week, we are focusing on the adjusted r squared. The idea is it's like all those different variables kind of influence the r squared in such a way, and so we have to adjust it to kind of make it a little bit more accurate. Really just focus on, like, when we're doing multiple regression, we need to focus on the adjusted r squared. That's what we're going to be looking at. And then also, of course, the f statistic is the is our test statistic that we're using for the r squared, and the p-value is tied to the it. Anyways, what I wanted to do is kind of show you like a graph. And so anyways, so what I did was you know how I said before, like this is like a multi-dimensional thing. It's going to be kind of hard to show graphs for this because the screen itself is 2-dimensional. So maybe we can give the illusion of 3 dimensionals, but it's going to be kind of hard, right? And also, if I do it like 4 dimensions, people are like, well, why isn't it time? And it's just, we're going to keep it simple and just keep thinking about the 2-dimensionals. So anyways, so what I have for here is, so I said, all right, how does the response compare with the predictors for x4 and x5, right? So looking back, we have x4 and x5 here, right? X5 has the really low p-value. X4 has the really high p-value, right? So looking at them, we have the red line is like thinking about like the slope that's kind of associated with the model that we created. So what I did was I pretty much just said from this model, I said, all right, for x4 and x5, we're going to create a line with the intercept, which is about 36, and for x4, the slope is going to be 0.95, whatever. And then for the other one, the one on the right, we have x5, the slope is still 36, or the intercept is still 36, and the slope will be negative 3.67329. It's the value right here, right? And so that's what those red lines are respectively. It's like in terms of x4 and in terms of x5. And the idea that I'm trying to show you is how well that model helps predict y based upon these individual predictors, right? And so notice the blue line, that's just where I did like the simple linear model with just those predictors. And those simple linear models predict way better than not like way better, but they predict better than the whole model itself. The one on the left for x4 is more noticeable than the one on the right. And so if you remember, let me kind of go back here. We said the lower p-value was for x5 and the higher p-value was for x4, right? And so notice that the red line definitely fits better for the one on the right than it does on the left, right? So it fits better for x5 than it does for x4. X4, remember, horrible p-value. Notice that red line doesn't fit that data that well. Whereas the one on the right, it fits way better, the one right up above me. So the idea is like, that's a lot of the sort of, so that blue line, that doesn't really have to do with that p-value calculation. That's just just to give you an idea for a best fit line for just that predictor and that response. Okay. Again, the p-value is like thinking about how well does that compare to 0. So also think about it this way, like with the one on the left, it's really close to 0, so it's not really predicting that much, hence the higher p-value, right? So anyways, the reason why I keep bringing this up is that when we're choosing our best model, we're trying to eliminate variables that aren't helping us predict that aren't helping the predictor or the response, right? We have these variables that we're calling predictors, but if they're not really helping us predict, then we don't really want to include them. And so we're trying to eliminate it and have more like X5 and less like X4. And so we have to have this process of doing that. And that's what I'm going to be talking to you about. Okay. So anyways, when we're choosing these best models, there's a few different ways that we could do it. And they're listed away in the text. And so like the first one, use logical selection based on educated guess. You've been in this class long enough. We're not going to do that. We can do better than that. We have such a powerful software. We gotta use it, right? So anyways, use principal components and factors analysis to it. That's a little beyond this class, so we won't be doing that either. Stepwise and backwards elimination. This is great. This is something that we can do. This is something actually I've done with other sections of 365 before, but we're not going to be doing this because what's going to happen with this is it's a process that it might eliminate possible combinations of variables prematurely. So the idea is like this bottom one, the one that we'll be actually using, is going to be testing out all these different combinations out and seeing which ones work, and it will come up with those different levels. And we'll kind of talk about like how it comes up with those different, or like how you can read those different models in just a second. But the idea is it's going to have a better probability of giving you better models than the one up above it with the stepwise backwards elimination. So really the bottom one is the one we're going to be focusing on. And by focusing on, that's the only one we're going to do today. All right, anyways. So the way that we do this is we create a subset object, and we use this method that is called reg subsets. And we put in the formula, and then we put in the data referring to the data frame reference, and then we want n best equal to 1. Okay? So the example, like I think it's in the walkthrough, it has, or the code that's given in the text. We have best subs is the object that we create. And this is using the car data sort of thing. And then once we create that object, we just put it into summary and it gives us data. What data does it look like? It looks like this. So really, I don't know how much of this you're going to find useful, but really it's that bottom part, the stuff that's like right over like here, that's going to be the most useful. And so what we can kind of think about is what these different models are. So this would be like, if we think about the different model numbers being the amount of predictors, model 1 would be where we use just X5. Model 2 would be where we do X1 and X5. Model 3 would be X1, X3, X5. Model 4 would be X1, X2, X3, X5. And the one where they're all, the best one with all of them would be all of them, right? So that's like where it picked. So what it just did, again, was it just picked the best only one predictor, the best only 2 predictors, the best 3 predictors, the best 4 predictors, and again, the best 5 predictors when they're out of 5 predictors. And so it tested all those different combinations to give you those values. And so that's important. So now, so what? So the idea is like now we use that subset object to kind of get an idea for which ones we like, and we use this subsets one. So then this would be the code that we use to get it. And when we run it, we get a in the plot area we get this right here. And a couple of things is like it kind of graphs out the different models out. So notice the X5, that's our model 1. Model 2 is, well, here you can kind of see. So this is model 1, 2, 3, 4, and 5. And it kind of it graphs them here. So this range right here, this Y range, is the adjusted R squared. Okay, and so the lower that model is for the adjusted R squared, the worse the adjusted R squared is. So it just found the adjusted R squared for those 5 models, and it said, here's how those best models compare with each other, right? And so the idea is like what we want to do is we want to choose the best largest R squared with the fewest amount of predictors. And this is where it gets a little gray because there's some subjectivity where maybe we give up a little bit of the adjusted R squared to get one fewer predictors. The idea is like that one that we're giving up isn't really helping to predict that much, right? We want to have like predictors that actually predict, right? And so maybe in giving up just a little bit of the adjusted R squared, we get a better predictor. And so that's what we like. The idea is like when we're coming up with these models for best predictors, having the fewer predictors can be useful because it's easier for calculations, whether it's for a computer or what. Or for a person calculating it. That could be a thing that we're considering it when we're trying to think of fewer predictors. That's just one of the reasons. The idea is like that's what we're going to be practicing, and it's going to be thinking about that kind of gray area as I walk you through choosing the best model of these 5. Okay, so anyways, I did a summary of each one of these 5, and I'm only going to fit 4 on a screen. So anyways, here are all those different models. So notice the model 1 is up at the top left. Model 2 is at the top right, up above me. Model 3 is over there, and Model 4 is right behind me, right? So we want to pick. So we have another one that we liked better. And so if you notice that the adjusted R squared, here's all the adjusted R squared just to kind of keep it in reference. Notice how much worse that adjusted R squared is for the one all by itself. Remember also with the graph where it was like really low, it's kind of a sign we don't like it very much. So I'm just going to eliminate this and say we're not even going to consider this. We're going to just look at these 4. So this is all 5 of them all together. So these are the 4 that we're looking at because remember, they're all have pretty close to the same adjusted R squared because remember that graph, they're all about the same level. So we kind of want to take into account which ones do we like the best. So let's kind of look at them. So let's see. Ooh, I don't want to make sure I use the right kind of pen for this. Let's see. So if we look at let's start from the biggest one and see which ones can we eliminate. So notice that we have 5 predictors here and we have 4 predictors here, right? Because this is model 5, this is model 4. And so this model 4 has fewer predictors. And it also has a better adjusted R squared because it's 0.26 or 0.826, and this is 0.22. So this has model 4 has a better adjusted R squared, and it has fewer predictors. So we don't want to consider this one either. Okay? So let's think about the next one down from that. So this is 3 because this has 3 predictors. This is model 3. Same sort of thing. It is slightly better adjusted R squared than 4, and it has fewer predictors. So we're going to not consider 4 anymore. Okay? Hopefully not the way you can kind of see it. And then when we look at the one at the top, so now we're looking between model 3 and model 2. So model 2 has a worse adjusted R squared because it's 0.8185, and the other one is 0.826, right? So really it's off by 100th or so. Like it's a little bit less than that, but 0.818 or 0.81, let's just do 0.8185 and 0.26. That's so close to each other. I mean, like you could round those to be like, this one would be like if we rounded it to the 100th place, it would be 0.83, and this one would be 0.82. So what we're giving up is, in order to go to 2, we're giving up one predictor or giving up 1/100th of a adjusted R squared to get rid of a predictor. So what I'm trying to say is this predictor, even though technically it makes a more accurate model, that having this value in here isn't really contributing much. So the value that we like the best, the model that we like the best is model 2, right? Because we're just giving up 100th. It's not that big of a deal. Even if it was a couple hundredths, whatever, easy. We have fewer predictors and a really good adjusted R squared that's really like pretty close to those other ones. Okay, so that's the one we like, and we'll come back to that in a little bit. Now, when we're thinking about assumptions, there's it has the same assumptions as simple linear regression, but we have to think about the multicollinearity, right? Because we have these different variables. We need to see the correlation between the different variables that we're comparing. So we want there to be a relationship with our with these predictors to influence our response, but we don't want them to influence each other because we're kind of wanting to isolate to try to predict the response itself. And when we have those, it muddies it. So the idea is like there might be there's probably going to be something there. It's kind of impossible to have nothing, and it's maybe kind of weird, but it's also like super weird for them to be totally collinear. That's also weird. But so the idea is like there's going to be that gap that we need to try to reduce. Okay. So anyways, so why do we care? So as it says here on the slide, collinear increases these 3 problems, right? Untrustworthy coefficients. These values don't represent the population, so which is kind of the point of what we're trying to do, right? We're trying to predict Y, but we don't really have these. They're not really, like I said, they're mudding the results. Because one of the things that's going on is it's limiting the amount of variability explained by Y, right? Because some of the variability can be explained in the changes between the X's, right? And we're wanting to explain Y. So it does that. And so it also helps, it prevents it interferes with the ability to assess the importance of each predictor, okay? Because they're kind of related to each other, okay? So anyways, we'll talk about 2 different ways that we have to find this collinearity. First is a correlation matrix, and the next is the VIF and the tolerance of the predictors. So first, let's talk about the matrix. So the method that we're going to be using is COR and then data, right? And you can't just put in your data frame. Well, you can't always put in data frame. Sometimes you can, but in ours, car data that's in the text walkthrough, you can't. And I'll show you that in just a second, but let me just go through the different ones. So the idea is you put the data in and it will say where the correlations are. And so for the different variables, we could select the different ones. And so notice for here, we have a comma with nothing before it. That's not by accident. That is totally on purpose because the idea is we're picking those columns of the data frame. And we want all the rows, so that's why there's nothing in front of it. So when we want all the things, we just have nothing. So it's that all the rows, comma, and then we say which of the columns we want, because that's the ones that we're specifying. And so you name them by name. But sometimes those columns are all together, so you could just say the range. And so you say data from 3 to 7. So that's saying the different column lengths. Now in the text, it goes from 2 to 7, and we'll see in just a second why that's not like that. So let's just go into R and take a look at all this stuff. So here I am in R. I already have some of these here. So we need to make sure we load all these things. I've already had them installed. And remember, when you're installing it, you just want to select that one and run it. Don't run multiple lines. Just when you're installing, just pick that one. I already installed it, and so that's what I did. And so I talked about all these, but remember the model that we like the most is the one with the X1 and X5, right? So I'm going to keep that one. Hold on to that one. So they call that B model 2. So notice, so here's the correlation matrix. So when we run this, it doesn't like it. The reason why is because when we look at car data right here, notice that model has some it's categorical variables. This is only really working when we're using just numbers. So really, it would only work with these. Okay. And so when we want to do, here's where I just pick the individual column. So run it. There it is. And then notice here, like before it was 2 through 7. So 2 through 7 is here's 2, 3, 4, 5, 6, 7. So 2 through 7 would be Y through X5. And the reason why I changed it to 3 is because we're wanting to find the collinearity between the predictors. Our models were helping us predict the relationship, the correlation with the whole model. So we don't want to include the response with that. So here I am finding it here, and notice it's the same values as we had before. Okay, so let's go back into the slides and take a look at this data. So we ran those values, and the thing to keep in mind is that what we're looking for is that the values are highly correlated. That means that they are, the absolute values of them are 0.8 or higher, right? So that means that it's either -8 or less, or negative 0.8 or less, or positive 0.8 or greater, right? If it's in those ranges, then we don't like that. So remember, this is what we came up with. I just copied this over. And so these are the ones that would actually make us feel uncomfortable. But if you remember back, the thing that we wanted, we liked, remember it was model 2 that we liked the best? So these are the what are tied to the model 2. So it's looking between, model 2 had just X1 and X5. And so notice that the corresponding values for X1 and X5 in the matrix, those are the yellow ones, those are under 0.85. So it's in that range that's greater than -0.85 and less than greater than -0.8 and less than 0.8, right? So it's in that middle range. So we like that, so that's good. So these other red ones, it doesn't even matter, okay? The other way that we could do this is using the VIF. So VIF stands for Variance Inflation Factor, and it's calculated in several ways. So the idea is like it looks at, like, let's say we're using 3 predictors, right? So X1, X2, X3. And it says, all right, And it creates these different models with them. So it says, all right, here's the formula for x1. We're gonna test out the how well it can be predicted by x2 and x3. And it says, all right, how can x2 be predicted by x1 and x3? And then finally, how can x3 be predicted by x1 and x2, right? And so depending upon what those adjusted R squareds, or those R squared, excuse me, are, will kind of affect that VIF. So the VIF itself is 1 over 1 minus that R squared, and then the tolerance can be found as the inverse of that, right? So it's a little bit of calculation, but remember, R does a lot of the work for us. So we have a simple method that we can use. You just have to make sure you have the car package. And so when you run the VIF, you put the model in there, and you want it to be less than 10, right? So if it's less than 10, that's great. Likewise, the tolerance, we want, that's 1 over that, the inverse of that, remember? So we want values that are less than 0.2. And if it's less than 0.2, it's a potential problem. If it's lower than 0.1, then that's a serious problem. Okay, so let's go into RStudio and take a look at this. So here I am in RStudio. Notice it's just VIF, and we're using that same model, right? That where it's x1 and x5. So we run it, and notice that the R squared is the same for both of them, and that it's less than 10, right? 10 was the magic number. This is 2 point something. That's definitely less than 10. So that's fine. And then the tolerance is 0.387703, right? Notice that this is not less than 0.2 and definitely not less than 0.1. So we're good, right? Which is what the matrix told us before. It was fine for the matrix, and now it's fine for this. Okay, so that's how you use both of those things. I think that is good for this, because I mean, like, the other stuff is just creating the models, which we did last time. Notice there's pluses in between the variables. I think that is good for today. Hopefully that's helpful. I'll see you all next week. Bye. Hey everyone, I hope you enjoyed that video. If you did, please press the like button below. It lets me know I'm doing something right. If you have any questions about any of the content, please send a message in Canvas to both me and the rest of the teaching team, and we'll get back to you as soon as possible. If you have any suggestions for how I can make these videos better, please leave in the comments below. Don't forget to roundhouse kick the subscribe button and ring the bell to get notified for when I post the next video. Anyways, I think that's good for this video. I'll see you all later. Bye.